the most valuable diamond ever found by a civilian in North America. Over 40 carats, flawless yellow, wasn't plucked from bedrock or blasted from a mine. It was picked up loose, lying in river-washed gravel that countless others had walked past. The truth is, nature doesn't label its most valuable stones. Diamonds in the wild almost never look like jewelry. And yet, one of the easiest ways to stumble onto something worth millions is also the most overlooked. Reading the silent signals in stream gravels and ancient riverbeds. When a diamond erupts to the surface, launched from deep mantle depths in a kimberlite or lamproite pipe, it doesn't stay put. Over millions of years, rain, wind, and gravity carry fragments down through the landscape. Diamonds are dense, around 3.52 g/cm superscript 3. That means they behave more like gold than quartz when water moves them. They sink fast, get caught in crevices, and cluster in low-energy zones, like inside river bends, behind boulders, or at bedrock contact points in paleochannels. Most people looking for sparkle in the wild are chasing the wrong trait. Real rough diamonds often look greasy, not glittery. They may be cloudy, coated with iron staining, or hidden inside nodules mistaken for pebbles. What separates them is habit, the natural form of the crystal, octahedral faces with sharp edges, dodecahedrons that look water-worn but geometrically regular, trigons, triangular surface growth patterns, visible under a loupe, are diagnostic and almost impossible to fake in nature. The first real test is sensory. In hand, a diamond feels heavier than quartz of the same size. Its luster, not glassy like quartz or vitreous minerals, tends toward an oily, almost wet-looking surface that doesn't wipe off. Under sunlight, it reflects internally in flashes more muted, but deeper than cubic zirconia or glass. But appearance isn't enough. The field test that changes everything is thermal conductivity. With a handheld diamond tester, less than $20 online, you can press the probe tip to a suspect stone and get an immediate reading. Diamond conducts heat extremely efficiently. Quartz does not. Most fakes, including high-lead glass and topaz, fail instantly. Moissanite, a common modern fake, can sometimes pass this thermal test, but gives itself away under a second method: electrical conductivity. Real diamonds are electrical insulators. Moissanite conducts. A dual-mode tester that checks both parameters decisively rules one out. Even without instruments, a focus collector can isolate strong candidates. Pan a gravel sample from a likely placer deposit. Use a number 20 mesh sieve, 0.85 mm openings, to eliminate coarse waste and focus on stones with visible habit. Scan for crystal faces. Test for weight in hand. If the stone doesn't scratch with quartz, Mo 7, and doesn't fog when you breathe on it, diamonds shed condensation almost instantly. It's a strong suspect. And if it's real, even an uncut diamond of 3 to 5 carats with good clarity and shape can fetch tens of thousands, or hundreds of thousands, depending on color and provenance. Fancy colors, pink, blue, vivid yellow, multiply the value exponentially. But before dreaming of sales, the key is identification. Because once you've found your first promising stone, the next question becomes, is it actually a diamond or just quartz with good PR? It's a common mistake with a heavy cost. You kneel down by a riverbank, spot a translucent stone with sharp edges, and toss it aside because it doesn't shine like a diamond. But that misconception, that all diamonds glitter in the wild, has led to more missed fortunes than perhaps any other. In reality, the rough diamond's natural appearance is deceiving, subdued, greasy, even slightly frosted. What matters isn't brightness. It's the combination of visual luster, crystal habit, and density. Traits that, when read correctly, sharply differentiate diamond from quartz, topaz, and other common misidentifications. Start with luster. True diamonds exhibit what's known as adamantine luster. a surface quality that's not just shiny, but sharply reflective with depth. Unlike the vitreous sheen of quartz, which reflects light in a shallow, clean way, diamond reflects light deeper within the crystal, with more contrast between light and shadow. In overcast light, this can appear almost oily or wet, especially if the surface is slightly weathered. That greasy look is actually one of the strongest field cues, especially when combined with non-symmetrical internal reflections. If a stone sparkles too evenly or glitters under direct sun, it's likely glass or cubic zirconia. Natural diamonds don't put on a show. They hide behind subtle physics. Next, consider habit, the natural geometry in which the crystal formed. Most natural diamonds form in octahedrons, 8 faces, cubes, 6 faces, or dodecahedrons, 12 faces. Some show combinations or are partially resorbed, leading to rounded edges. What's key is symmetry. A diamond crystal, even heavily worn, tends to hold its basic angular identity. Look for triangles, especially trigons. Microscopic triangular pits etched onto the crystal faces, often visible only with a 10x loop. Trigons are unique to diamond. No other natural mineral forms them at this scale and symmetry. Their presence is one of the most reliable visual confirms short of instrument testing. Now test by feel. Quartz, even when large, feels lighter than diamond because of its lower specific gravity, about 2.65 versus diamond's 3.52. This weight in hand difference becomes noticeable with practice. A 5 mm quartz fragment may feel hollow compared to a similarly sized diamond, which has a satisfying, compact heft. This is particularly helpful when comparing multiple gravel specimens side by side after panning or screening. But be careful. Moissanite and high-lead glass can mimic weight. That's where hardness comes in. Diamond ranks 10 on the Mohs scale. Nothing natural can scratch it. With silicon carbide sandpaper, Mohs 9.1. Moissanite will show faint wear after a few strokes. Quartz scratches easily by comparison. A cautious field hardness test involves rubbing the edge of your suspect stone against a corundum tile, sapphire, Mohs 9. Diamond should leave a line. Quartz will wear instead. One final note. In sunlight, diamonds often show color flashes, but not the full rainbow fire of cut stones. If your rough stone throws dramatic color, especially in reds and purples, it's more likely zircon, which also has a high specific gravity and is a common false positive. Zircon crystals are often prismatic and double refractive. Under loupe, their facets blur or double up. Diamond, being singly refractive, keeps its internal lines crisp and singular. A clear sign when you're hunting precision. Learning to recognize these traits is like tuning your senses to a hidden frequency. You stop judging based on sparkle and start reading shape, density, and luster. And once that shift happens, a whole new world of potential opens up, especially when you start tracking where these stones are coming from. Which raises the next question. How do you find the terrain that actually produces them? There are diamonds in rivers that no longer flow. That's not poetry, it's geology. Many of the richest diamond-bearing zones in history weren't found in roaring streams or fresh channels. They were uncovered in dry, grassy fields where the river vanished thousands to millions of years ago. These ancient riverbeds, called paleochannels, act like time-locked conveyors, capturing diamonds when they moved, then preserving them long after erosion patterns shifted. And in countries like South Africa, Brazil, Australia, and parts of Canada, these invisible rivers still feed the global market quietly, stone by stone. Finding them begins with a mental reset. We're trained to follow modern water, but in diamond country, that can be misleading. Over geologic timescales, rivers migrate, meander, and abandon old paths. The key is identifying features like low, sinuous ridges or color shifts in satellite imagery where finer sediments once flowed. In places like the Vaal River Basin, entire fortunes were made by tracing relict stream beds buried under just a few meters of overburden. Even a slight depression with rounded gravels and patches of black sand, away from the current watercourse, might signal a paleoflow. So how do you prove it in the field? Start with coarse gravel. Paleochannels preserve rounded quartz cobbles with interbedded sand and clay layers. If you find heavy minerals like ilmenite, garnet, or chromite embedded between these gravels, you may be sitting on an ancient trap point. Diamonds, being both dense and hydrophobic, tend to concentrate at the bottom of such deposits, right at the interface with impermeable clay or bedrock. That's where you dig. Use a trench or auger sample down to this basal contact. Collect the lowest 30 centimeters of material and pan it carefully, watching for heavies. If magnet sweep shows ilmenite and garnets are angular with deep red to purplish hues, you may be dealing with erosion remnants from a distant kimberlite or lamproite pipe. Even if the source is no longer visible, the payload, diamonds, remains held in place by time and geology. In regions like Minas Gerais, Brazil, many river systems have long since dried, but their sediments remain tucked under hill slopes and terraces. Old miners learned to chase the cascalho, the gravel zone that often sits just a meter or two below surface, and test it not by appearance, but by concentration. In the Argyle Field of Australia, paleochannel mapping was what turned a remote scrubland into one of the world's top-colored diamond producers. The trick is perspective. Diamonds don't care about our maps or current rivers. They move according to gravity, water velocity, and density sorting, all governed by physics. Once you understand that, the landscape becomes a code. Dry gullies, abandoned meanders, even plowed fields could hold concentrated deposits missed by generations of surface-only prospectors. But once you identify the right terrain, the question becomes sharper. Are the minerals pointing to a local source, a diamond pipe nearby, or just distant travelers? That's where indicator suites come in, and they tell a story the naked eye can't. A single diamond in the pan is exciting, but a pan full of the right indicators is far more valuable, because it suggests the presence of a diamond source still intact, upstream or uphill. In professional exploration, before a single core sample is drilled, geologists comb the terrain for specific heavy minerals known as indicator minerals. These aren't just random trace elements. Each one is a genetic fingerprint, linking surface sediments back to a volcanic source, typically kimberlite or lamproite, that once erupted diamonds from the Earth's mantle. Read correctly, they can lead you straight to a buried fortune. 3 indicators dominate the field: pyrope garnet, chromite, and ilmenite. Each has its own formation environment and diagnostic traits, and together, they form a suite that strengthens the case for diamond presence dramatically. Start with pyrope garnet. Unlike the ruby-red almandine garnets common in schists and beach sands, pyropes linked to diamonds are magnesium-rich and often show a distinct pink to purplish hue. Under magnification, they may fluoresce in orange to reddish tones under shortwave UV. But more importantly, they exhibit high specific gravity, 3.6 to 3.9, and are often sharp-edged, suggesting limited transport and thus proximity to source. In classic fields like Siberia's Yakutia or Canada's Slave Province, pyrope garnet concentrations often increase as one moves toward undiscovered pipes. Next is chromite. Diamond-associated chromites are dense, black to dark brown, and strongly magnetic, a key trait for field isolation. When swept with a neodymium magnet, they respond instantly, often clustering with ilmenite in pan concentrates. Chromite resists chemical weathering and tends to remain even when diamonds have been leached or redeposited elsewhere. Their persistence makes them excellent long-range pathfinders. Ilmenite, a titanium iron oxide, is the third piece of the suite. It appears black, metallic, and magnetic, but its real value comes from surface chemistry. Diamond-favorable ilmenites often show signs of high oxidation, a crusty or etched surface. These surfaces interact with fluids in the mantle, and their composition can indicate whether the rock they came from was fertile, meaning capable of carrying diamonds. In lab settings, ilmenite's geochemistry is assayed via electron microprobe to detect favorable trace element signatures. In the field, high density, submetallic luster, and sharp crystal faces are practical proxies. The strength of the indicator suite comes from co-occurrence. Finding one of these minerals alone could mean anything. Finding two increases the odds. Finding all three, especially with consistent upstream concentrations, is a red flag that something larger sits hidden nearby. That's why field teams establish sampling grids, collecting 10 to 20 kilograms of material per site, sieve through number 20 or number 40 mesh, then process through heavy liquid separation or panning to isolate the heavies. Map those points, and patterns emerge. A consistent upstream concentration increase indicates directionality. Fluctuations suggest secondary deposits. But when indicator counts spike and diamond finds begin to appear in proximity, the conclusion is unavoidable. You're in the halo of a diamondiferous pipe. But before drilling, or even trenching, there's a smarter path. A first-pass test suite that lets you isolate stones worth deeper analysis with basic tools. Because once indicator minerals point the way, you need to decide what samples to trust, and how to eliminate the fakes before wasting time or money. Before you spend $1 on lab assays, drone surveys, or claims registration, there's a triad of tools that every serious diamond prospector should master: a neodymium magnet, a 10x loop, and a well-worn gold pan. These aren't just starter gear. They're precision instruments when used correctly, able to filter false positives and spotlight high-potential targets long before any formal testing is needed. Most field discoveries start right here, with wet hands, coarse grit under your nails, and a few small clues in the bottom of a pan. Begin with the pan. Whether you're working modern stream beds or dry-sifting paleo-channel gravels, the goal is the same: isolate the densest fraction. Diamonds sink fast. So do their indicator companions. Use a mesh sieve, number 20, 0.85 mm, or finer, to screen your sample before panning. Discard the light floaters and focus on what settles last. If you're seeing heavy black minerals clustering at the bottom ridge of the pan after washing, you're close. This is where the magnet comes in. Sweep a small neodymium magnet just above the wet concentrate. Magnetite will leap to it, but more importantly, so will ilmenite and chromite, two members of the diamond indicator suite. Their magnetic response is often your first hard clue that the source terrain is kimberlitic in nature. Unlike ferromagnetic debris from industrial or volcanic contexts, ilmenite grains tend to be more stable, dull metallic, and subangular. If garnets appear too, deep red, glassy, heavy, then you've assembled a suite worth tracking upstream. Next comes the loop. Use it to assess crystal habit and surface features. Diamonds, even in rough form, retain their morphology: octahedral edges, trigon pits, and a subtle greasiness to the surface. Glassy imitations tend to chip unevenly or show flow textures. Quartz may have conchoidal fracture, but lacks the angular regularity. Under 10x magnification, watch for doubling of facets, a giveaway for moissanite, which is doubly refractive. Diamonds are singly refractive and maintain crisp facet edges under magnification. With the loop, also inspect garnets. Pyrope garnets suitable as diamond indicators show vibrant color, but most importantly, a transparency uncommon in metamorphic garnets. Chromite appears jet black and may show tiny fractures or metallic sheen under close inspection. These visual confirmations build the case before lab verification is ever needed. This field toolkit isn't a replacement for lab work, but it lets you prioritize where to focus. In areas with thousands of square kilometers of terrain, knowing which 50 meters to sample again could mean the difference between a discovery and a miss. It also guards against high-cost mistakes. Chasing quartz, mistaking slag for magnetite, or hauling glass simulants miles out of the bush. Many a field crew has returned empty-handed because they failed to confirm basic signals before committing to logistics-heavy follow-ups. But even when a stone passes the magnet, loop, and pan tests, you still need to watch for the cleverest of fakes. Because in high-grade zones, nature isn't the only source of deception. Some stones are almost perfect until you test them thermally. It looks right, feels right, even passes the magnet sweep, and sits heavy in the pan like it belongs. But what many field hunters don't realize is that some of the most convincing diamond imposters, especially moissanite, are engineered specifically to mimic every visible trait of rough diamond. In markets flooded with simulants, and even in second-hand gravel from old claim sites, the only thing standing between a prospector and a costly misidentification is a small, portable device, the thermal conductivity tester. And if you want certainty, pair it with an electrical probe. Here's why it matters. Diamond has the highest thermal conductivity of any natural material, 5 times that of copper. That means it draws heat away from a test probe so fast that thermal testers instantly register it as diamond. Quartz, topaz, and glass don't come close. You can hold a suspect stone in your hand, press the tip of the tester to its surface, and get a fast result. A diamond will beep or light up almost immediately. But here's the problem. Moissanite, or silicon carbide, conducts heat nearly as well. It will often fool basic thermal testers, especially older models. This is why many lab-confirmed diamond fakes sail through initial field screens. Moissanite is doubly refractive, which can be caught under a loupe. But in rough form, it still closely mimics octahedral crystal habit and specific gravity. It feels right. It even scratches quartz. And it's cheap enough that some unscrupulous sellers scatter it deliberately in field spoil to bait buyers. The solution? Electrical conductivity. Diamonds are electrical insulators. They don't conduct current. Moissanite does, often strongly. Newer testers combine thermal and electrical probes into a single handheld unit. In under 10 seconds, you can identify a stone as a true diamond, thermal positive, electrical negative, or eliminate moissanite, thermal positive, electrical positive. These dual testers are now essential for serious field identification, especially in areas with high fraud risk or mixed material. But there's a nuance worth noting. Natural diamonds with significant inclusions, especially graphite or metallic sulfides, can sometimes show borderline electrical activity. That's why multiple tests matter. Cross-reference conductivity with visual habit, weight, and hardness before making a final call. For those working without electrical gear in remote zones, there's still a fallback. Breathe on the stone. Diamonds disperse condensation faster than any other material, usually within 1 second. Moissanite and quartz hold fog longer. It's not definitive, but paired with thermal results, it adds another layer of confidence. Don't underestimate the payoff. A 5-carat moissanite might cost $100. A 5-carat uncut diamond of good clarity and color can easily top $50,000. And exponentially more for fancy colors. One mistake in the field, and your entire valuation collapses. Yet with a $50 dual tester and some methodical checks, you turn guesswork into evidence. Still, identifying the stone is just half the job. You also need to extract it, and the tools you use, especially your mesh size and panning method, determine whether that million-dollar diamond ever even makes it into your hands. The stone you're after might already be in your sample. But unless you understand mesh size and its effect on concentrate recovery, you could literally wash it away without ever knowing. Diamonds don't announce themselves with size alone. In many placer deposits, especially older or highly eroded terrains, the diamonds preserved are small, sub-carat to 2-carat range. But some are flawless, and their per-carat value can eclipse larger, flawed stones by orders of magnitude. Precision sieving is what makes or breaks your ability to recover them intact. Let's break it down. A standard mesh screen is graded by the number of openings per linear inch. A number 20 mesh screen has openings of approximately 0.85 millimeters. A number 40 mesh is finer, around 0.425 millimeters. In diamond prospecting, these numbers aren't academic. They determine your cutoff for what gets saved and what gets flushed out. Many amateur panners use only one sieve or none at all, relying on eyesight or pan skill alone. The result? Stones smaller than 1 mm, often the most perfect and valuable per carat, vanish with the tailings. Experienced prospectors layer their screens. A coarse top layer to remove waste cobbles and sticks, then sequential mesh sizes, typically number 10, number 20, and number 40, to sort material by density and dimension. After panning each fraction separately, the heaviest and smallest stones settle in the lowest ring of the finest mesh. That's where microdiamonds and near-gem quality particles collect. In kimberlite exploration campaigns, these fine fractions are routinely processed in bulk, sometimes tons at a time, because a single high-grade microdiamond can justify drilling. But mesh size does more than preserve tiny stones. It also reveals textural and shape information. Diamonds trapped in the #2040 window are often angular, resistant to abrasion, and maintain partial crystal habit, signs of limited transport. In contrast, rounded quartz and zircons that pass through finer mesh lack those edges and frequently show water wear, helping you dismiss them quickly under loupe. If you're using only a number 20 mesh, you'll retain larger indicators and macrocrystalline candidates. This is good for finding octahedrons, dodecahedrons, and coarse garnets. But skip the finer mesh, and you miss the full suite, especially smaller chromite grains and tiny pyropes that concentrate together. These build statistical weight. If you find 5 garnets above 0.85 millimeters, there may be 50 below it, silently confirming the source's fertility. Water flow technique also matters. Don't over-agitate. Diamonds are heavy, around 3.52 g/cm superscript 3, and will settle with a gentle rocking motion. Too much force, and they ride the overflow with organics. Use a gold pan with a controlled swirl, letting the lighter sands roll off while keeping the base layer pinned. Add a small squirt of biodegradable surfactant or dish soap if necessary to reduce surface tension. This prevents flat flakes from floating, and if you're in a dry environment where water is limited, air sieving can work with vibration screens. Use a gentle blower and layered mesh system to sort concentrates into grain bins for later wet processing. This is how exploration crews in arid zones like Western Australia or Central Africa screen for diamonds with minimal water usage. Mesh isn't just a filter, it's a gatekeeper. Without the right size, you lose the stones you came to find. And once they're gone, you won't know they were ever there. But even when your pan holds a glimmering candidate, how do you know it's not just zircon, topaz, or glass, all of which can mimic diamond under the wrong conditions? You pan out the final concentrate, and there it is, a sharp-edged crystal, slightly greasy, dense, and throwing a ghostly blue glow under your UV torch. For a moment, it feels like discovery. After all, diamonds fluoresce, right? Yes, but so do dozens of other minerals, and one in particular has fooled more field collectors than any other: zircon. Zircon is dense, often colorless or light brown, and forms in well-shaped, often prismatic crystals. Under long-wave ultraviolet light, 365 nanometers, many zircons emit a blue to yellowish-white glow that closely resembles the bluish fluorescence common in natural diamonds. Some even show internal zoning and fracture patterns that, to the untrained eye, mimic rough diamond structure. Worse, zircon's specific gravity, 4.6, 4.7, is even higher than diamond, meaning it concentrates in the same pan layer, behaves similarly underwater, and stays put during panning or sluicing. That's why relying on UV fluorescence alone is a dangerous shortcut. While approximately 30 to 40% of natural diamonds fluoresce, typically in blue, it's not a definitive test. Some do not fluoresce at all, while others glow yellow, orange, or even green depending on nitrogen impurities or strain. In contrast, zircon's glow is often stronger, sustained, and sometimes includes phosphorescence, lingering glow after the UV source is removed, which diamonds almost never show. But these distinctions aren't always obvious in the field. So how do you separate them? First, inspect the crystal habit. Zircon often grows in tetragonal prismatic forms, long, columnar shapes with flat terminations, distinctly different from the octahedral or dodecahedral habits of natural diamonds. Under loupe magnification, zircon may display horizontal striations or fine cleavage lines. Diamonds lack cleavage faces visible in hand specimen and tend to resist chipping in a predictable way. Next, consider double refraction. Zircon is strongly birefringent. It splits light into two paths. Under loupe or microscope, this causes facet edges to appear doubled or blurred, especially at oblique angles. Diamond is singly refractive. Its internal lines stay sharp. Moissanite also doubles, which makes this check useful across imposters. A scratch test can also help. Diamond ranks 10 on the Mohs scale. Zircon sits at around 6.5 to 7.5 and can be scratched by silicon carbide, used in many sandpapers. Gently testing an inconspicuous edge can reveal whether your candidate resists abrasion. Be cautious. Destructive tests should only be done on suspected low-value material or with extreme care. Zircon's presence isn't always bad news. In some terrains, it co-occurs with kimberlite indicators, and its abundance can help confirm a mantle-derived sediment source. But unless paired with pyrope garnet, chromite, or ilmenite, it's not diagnostic of diamond pipes. And when found as lone crystals glowing brightly in UV, it's more often a distraction than a discovery. The key lesson? Fluorescence is a support test, never a primary method. It can eliminate fakes that don't glow. It can hint at structure, but it cannot confirm value. Diamonds that don't fluoresce are still real, and stones that do, especially if they look too clean, too perfect, or too bright, are often just well-formed lies, which leads to a deeper mystery. What happens when a sample assumed to be quartz, scratched, ignored, even discarded, comes back from testing as something else entirely? That's the kind of reversal that reshapes the entire search area. It sat in a jar for months, a cloudy, lusterless fragment, sharp-edged but uninspiring. Initially mistaken for quartz, it passed through sieves, resisted a weak scratch test, and sat unloved at the bottom of a mineral tray until one final test. A full specific gravity run changed everything. The result? 3.52 G/cm superscript 3, almost exact for diamond. A second opinion from thermal conductivity confirmed it. What had been dismissed as an unremarkable crystal turned out to be a rough, pale gray diamond. 2.1 carats, natural, octahedral, and flawless under loupe. That one stone, overlooked and nearly discarded, was appraised at over $40,000 uncut, and the implications were larger than the find itself. This kind of reversal is not rare. It's routine in early-stage exploration. Many naturally occurring diamonds don't look like gemstones. They lack transparency, are coated in iron oxides, or present irregular surfaces due to resorption and transport. Field identification under pressure and fatigue means even experienced hands mislabel stones, particularly when they mimic the more common traits of quartz: transparency, hardness, and a lack of visual sparkle. But quartz and diamond diverge dramatically when you bring out proper instrumentation. The scratch test, long considered gospel in the field, fails when done without precision. Quartz can scratch glass. Diamond shrugs off most abrasion, but can chip if struck at the wrong angle. This overlap leads many to assume hardness confirms identity, a dangerous assumption. The lab reversal began with specific gravity. Quartz sits around 2.65 g/cm superscript 3, while diamond is noticeably denser at 3.52 g/cm superscript 3. Using a simple water displacement method, weighing the stone in air and again submerged in water, a prospector can compute this value with surprising accuracy using only a scale and a beaker. When the number came back anomalously high, it raised enough doubt to justify further analysis. The next step was thermal conductivity. The stone passed instantly, indicating high thermal transfer, consistent with diamond, but still potentially moissanite. So they tested electrical conductivity. The stone failed, meaning it did not conduct electricity, a key diamond trait. Moissanite would have passed both. Finally, under UV light, the stone showed a faint bluish fluorescence, common in about 30% of natural diamonds, but not definitive. The clincher came under magnification. Trigons, microscopic triangular etchings, visible across one surface. Trigons are exclusive to natural diamonds and form as a result of slow crystallization in mantle conditions. They are not found on quartz, glass, or simulants. The error highlighted a persistent risk in fieldwork: reliance on visual familiarity over data. Had this sample been tested earlier, or recorded with full grid coordinates, the source terrain might have been delineated sooner. Instead, months passed with key indicators missed, and a potentially fertile pipe sat unexamined in the background. But the discovery did more than validate the stone. It reframed the entire sediment profile of the site. Suddenly, previous finds of pyrope garnet and magnetic chromite weren't just geological noise. They were part of a larger system. The reclassification triggered a reassessment of upstream terrain, leading to expanded grid sampling and the eventual identification of an eroded kimberlite still partially exposed along a terrace. The value of the find wasn't just the diamond. It was the shift in interpretation. These reversals, where overlooked, misjudged, or discarded material turns out to hold extreme value, are the quiet pivot points of diamond fieldwork. They underscore a truth that separates casual prospectors from strategic ones. If you don't test, you don't know. And when you do, even a dull stone can turn the entire field on its head. The next step is understanding what you're really looking for. Not just stones or sediments, but the volcanic structure that makes diamond transport possible in the first place. Because without a kimberlite pipe, even the richest indicator suite is just smoke without fire. Every diamond ever worn, traded, or cut into brilliance began the same way, in a violent, ultra-deep volcanic event unlike anything currently observed on Earth. These eruptions formed the geological structures known as kimberlite pipes, the primary delivery system that brings diamonds from the upper mantle to the surface. Understanding how these pipes form, erode, and distribute material is key to locating untapped sources. Because while diamonds can travel, their story always starts in a pipe. And every alluvial or placer discovery is merely a shadow of that explosive origin. Kimberlite pipes are carrot-shaped intrusions formed by gas-charged magma, erupting at speeds exceeding 900 kilometers per hour. These eruptions originate at depths of 150 to 250 kilometers, where carbon-rich fluids exist under extreme pressure. The release is sudden, forming vertical conduits filled with a mix of ultra-basic melt, xenoliths, fragments of deep rock, and, if conditions align, diamonds. The explosion excavates a crater several hundred meters across, with volcanic debris settling into a classic diatreme or volcanic neck. But diamonds are fragile passengers. Only certain eruptions preserve them. The melt must ascend quickly enough to avoid excessive heat or pressure changes that resorb the crystal into graphite. That's why not all kimberlites are diamondiferous, and why mapping the pipe's structure and mineral assemblage matters. Over millions of years, most pipes erode. What remains on the surface are crumbled edges, weathered breccias, and the occasional dike or sill feeding into overlying sediments. This is where stream activity begins. Rain and gravity wash the surface, breaking down kimberlite matrix and freeing the heavy minerals. Pyrope garnet, ilmenite, chromite, spinel, and in rare cases macrodiamonds. These materials travel downslope, concentrating in streams, gulches, or terraces. The farther they go, the more the diamonds decrease in size and the indicator sweet fragments, unless erosion is recent or terrain traps them close. Finding diamonds in stream beds, then, is a chase in reverse. You're not looking for the stone itself. You're tracking the path back to its eruption point. That's where understanding crater logic matters. Pipes tend to occur in clusters or fields, often aligned with deep crustal features or ancient fault zones. In Canada's Lac de Gras, over 150 pipes form a dense field. In South Africa, the Kimberley cluster sits along a Precambrian lineament. These alignments can be inferred from magnetics, but they also leave physical clues. Odd hills, ultramafic float, or high-density sediments near the surface. In tropical or temperate zones, erosion can completely strip the crater, but leave kimberlite float. Angular, chalky fragments with high magnesium and serpentinization spread across the surface. A quick acid test, dilute HCl, on kimberlite shows fizzing from carbonate weathering, while true basalts or andesites typically remain inert. This lets you quickly differentiate between diamond-bearing pipes and volcanic imposters. Understanding erosion also helps gauge whether a pipe has been mined before. Deep erosion may remove the upper crater, exposing richer diatreme material. Minimal erosion may leave the pipe mostly buried, with just a hint at the surface, a scattering of indicator minerals, a strange hill, or anomalous vegetation due to altered soils. In cold climates, permafrost may preserve pipes near the surface. In arid zones, erosion can reveal pipe margins through color contrast and mineral staining. The strategic insight is this: stream diamonds are a symptom. The pipe is the disease. Every diamond in the water came from a place, and that place, if still intact, may hold thousands more. But not all pipes are equal. The rock that hosts them, kimberlite or lamproite, can change everything about quality, quantity, and market value. Not all volcanic pipes are created equal. Some are diamond-bearing in name only, exhausted, low-grade, or chemically hostile to crystal survival. Others erupt fewer stones, but yield spectacular color and clarity that command extreme premiums on the market. At the core of this difference are two host rocks, kimberlite and lamproite. Both can transport diamonds, but they differ in chemistry, structure, and, most importantly, the type and quality of diamond they're likely to preserve. Kimberlite is the more common host, responsible for over 90% of known diamond pipes globally. It's an ultra-basic, volatile-rich igneous rock, often highly serpentinized and composed of olivine, phlogopite, and accessory minerals like ilmenite and chromite. When fresh, it has a blue-gray color and clayey texture, hence the term blue ground. Upon weathering, it turns yellowish or ochre, forming the so-called yellow ground often mined in open pits. Kimberlite's explosive ascent and high magnesium content make it ideal for transporting diamonds fast and cold enough to preserve their integrity. But its quality varies wildly. Many kimberlites are barren or contain microdiamonds with no commercial viability. Lamproite, by contrast, is rarer and more selective. It's a potassium-rich volcanic rock that often erupts through deep crustal weaknesses in ancient terrains. Structurally, it contains rich concentrations of leucite, sonidine, and apatite, and is chemically more reactive than kimberlite. This reactivity means that in some pipes, diamonds dissolve or alter before reaching the surface. But when conditions are right, high-pressure ascent, short eruption time, and low oxidation, lamproites can produce extraordinary stones. Case in point, the Argyle mine in Western Australia, a lamproite pipe discovered in the 1970s, it became the world's largest source of pink diamonds, stones that command prices exceeding $1 million per carat for top grades. Argyle's geology is unusual. Despite relatively low diamond content per ton of ore, 3-4 carats, the coloration and saturation of its fancy pinks, purples, and reds changed the global market. These colors are linked to lattice distortion from intense mantle pressure, a feature preserved thanks to lamproite's rapid ascent and unique chemistry. Field identification between the two hosts is subtle but possible. Kimberlite tends to fizz mildly with dilute hydrochloric acid due to carbonate content. Lamproite often reacts more vigorously because of higher levels of secondary alteration. Both are magnetic to varying degrees, due to ilmenite and magnetite, but lamproite float can be more friable, with softer, clay-rich textures. Under a hand lens, lamproite may show aligned mica flakes and feldspathic material not common in kimberlite. In terms of indicator minerals, both rocks share some similarities: garnet, chromite, and ilmenite. But lamproite fields may lack strong pyrope signatures and instead show distinct perovskite or apatite inclusions. This complicates traditional indicator tracking, requiring lab-based geochemistry to confirm fertility. However, when diamonds are present in lamproite, they often show higher clarity and a wider range of colors, particularly in fancy hues. From a commercial standpoint, kimberlites are more predictable but yield mostly near colorless stones, suitable for industrial or gem-grade production. Lamproites are unpredictable, but when they pay off, they do so explosively, often with low tonnage and high value per carat. This shapes how exploration proceeds. Kimberlite discovery triggers bulk sampling and tonnage modeling. Lamproite demands microscale screening and early value appraisal, especially for color. Diamonds originate in some of the oldest and most stable parts of the Earth's crust, cratons. These thick, ancient continental cores provide the perfect pressure and temperature conditions for diamond formation and preservation. Around the world, these regions are not randomly distributed. They're geologically mapped and have proven records of diamondiferous activity. In Canada, the Slave Craton hosts multiple kimberlite fields, including some of the richest recent discoveries. In Brazil, the São Francisco Craton has produced diamonds both from primary pipes and secondary placers. The West African Craton spans multiple borders and has fed alluvial deposits for centuries. Russia's Siberian platform is home to massive pipes that have supplied global markets for decades. Even Australia, though less prolific today, once led the world in volume thanks to its lamproite fields. Identifying these terrains narrows the global map to the zones where serious prospecting begins. When one pan shows indicators or even a diamond, the goal isn't to celebrate, it's to systematize. A grid is laid over the terrain, often in 50 to 200 meter spacing, depending on the geography and the density of prior finds. At each node, consistent sampling is performed, 10 to 20 kilograms of sediment, sieved and panned identically to maintain data integrity. Each result is tagged with coordinates, elevation, and basic terrain features. As samples are processed, indicator mineral counts are plotted. Where garnet, chromite, and ilmenite values spike, the direction of probable source becomes visible. Repeating this process over tighter grids allows refinement. Ultimately, it builds a map, not of the land, but of the mineral signal beneath it. The clearer the gradient, the closer you are to the origin. In the field, false positives waste time and money. That's why even without a lab, 3 simple tests help rule out pretenders. First, the acid test. Diluted hydrochloric acid applied to a fresh rock surface will fizz slightly if the rock is kimberlite, due to its carbonate content. Basalts, lavas, and most volcanics won't react. Second, the UV test. Some altered kimberlites fluoresce weakly, but true volcanic imitators often display inconsistent or strong reactions under long-wave UV. A subtle but useful differentiator. Third, the hardness test. Kimberlite typically falls around 4 to 5 on the Mohs scale. If a rock resists scratching from a knife or steel, it may not be kimberlite. These quick field screens don't replace lab work, but they sharpen your sample set and help direct serious effort toward likely candidates. The value of a diamond is not in its size alone. A 1-carat rough with excellent color, clarity, and octahedral symmetry can be worth more than a 3-carat stone with internal fractures or cloudiness. Most gem-grade diamonds fall into the colorless range, but stones with strong fancy hues, pink, blue, yellow, command extreme premiums. Clarity also drives value. Inclusions, especially near the surface or aligned with cleavage planes, can drastically reduce yield during cutting. Crystal habit matters more than most realize. A well-formed octahedron retains more weight during faceting, increasing the cut potential and market price. Even in the rough, buyers assess a stone not only for size but for angle, symmetry, and the way it reflects internal light. Understanding these drivers transforms a raw find into a strategic asset. No matter how rich the terrain or promising the pan, nothing proceeds legally without proper access. In most diamond-bearing countries, prospecting rights are regulated. These can range from simple landowner permissions to complex government-issued licenses, depending on the jurisdiction. Ignoring this framework risks seizure of fines, loss of claim rights, or legal action. It also jeopardizes future exploration work. Responsible field teams file permits, respect indigenous and private land, and understand the implications of each step, from sampling to staking. Some zones require environmental clearances before trenching. Others need declaration of fines within specific time windows. Legal groundwork doesn't just protect your work, it legitimizes it, especially when transitioning from exploration to development. Field success can vanish in the negotiation room. Many prospectors, flush with excitement after a find, rush to sell rough without proper valuation. This opens the door to underpricing, fraud, and fakes. Common tactics include glass fragments or synthetic moissanite seeded into mixed bags, used to devalue the real stones or confuse the seller. Lowball offers often rely on urgency, claims that the market is soft or the quality is questionable. Without independent lab reports, certification, or trusted gemological networks, a stone worth 6 figures can sell for 10% of its true value. Patience is protection. Verification, slow due diligence, and trusted intermediaries turn raw material into wealth. When doubt lingers, comparison brings clarity. In one field case, a suspected quartz fragment had all the wrong appearances: cloudy, edge-worn, low luster. But testing said otherwise. Specific gravity pointed to 3.52. Thermal response confirmed conductivity. Electrical test returned a negative, ruling out moissanite. Under loupe, it showed trigons and a greasy surface. A confirmed reference diamond, brought out for contrast, showed near-identical features. The side-by-side visual sealed it. That moment moved the stone from curiosity to confirmed asset. It also validated the surrounding indicators and triggered further sampling. One match doesn't just prove a stone, it justifies a grid, a trench, and a permit. That is the turning point from theory to action. Once a stone tests positive and passes valuation, a new set of decisions begins. Do you keep it raw, leveraging rarity and shape for a higher price to rough buyers? Do you cut it, accepting weight loss for the potential of brilliance and market impact? Do you partner with an established operator, trading control for infrastructure and scale, or license the find itself, turning your data and coordinates into royalties from a larger mining venture? Each path has consequences. Cutting exposes flaws, but can unlock massive value. Selling rough may forfeit upside, but guarantee liquidity. Licensing may delay payoff, but reduce risk. The best route depends on the size, quality, and uniqueness of the stone, and the strategy behind the discovery. Finding a diamond in nature is not about chance. It's about attention, the ability to see what others step over, to run tests others skip, to follow a garnet upstream when everyone else walks downstream. Every million-dollar stone begins the same way, with sediment in a pan and a decision to look closer. Process makes the difference. Sieve size, grid spacing, indicator tracking, test layering. Luck may spark discovery, but method brings it home. And in the end, the sharpest tool isn't the loop, the magnet, or the pan. It's the practiced eye that knows what not to ignore.